So it's a pleasure for me to be a speaker in this exciting workshop. It's really a lot of new insight that were introduced. And today I would like to continue with development of new tools for NMR at nanoscale, with particular focus on applications in zero or low magnetic fields. And this is a collaboration between our team in Ulm and theory group at Ulm University, Martin Plenio, Alex Rezka at Hebrew University, and on experimental side, Mikhail Lukin at Harvard, Eli Schwartz and Philip Neumann at Envision, and Dima Budkar and John Blachar at Mainz University and Helmholtz Institute. So that we had already a talk basically motivating NV centers magnetometry as tool for nuclear magnetic resonance. I just would like to highlight again that conventional NMR has certain drawbacks related to sensitivity. Typically, you use a coil for detecting magnetization, and you work with thermal polarization of spins, and there is a source of noise related to conventional coil, and also limited signals available at thermal polarization conditions. And basically, improving NMR sensitivity means improving detection, replacing coils, for example, by magnetometers, and improving polarization by going beyond thermal. I will touch a little bit in my talk both sides, making better detectors and making new or developing new polarization techniques. And these new detection methods are going along with different research avenues like squid magnetometers, atomic vapor magnetometers that were introduced yesterday very nicely, force detected NMR, and relatively new player in this field, NV centers magnetometers. And in the very end, I would like to touch also a little bit hyperpolarization with NV centers. I guess I don't need very large introduction into NV centers. It was introduced by Dima Budkar yesterday. Just want to tell you that it's somehow a unique solid-state system that connects optical photons and microwave photons, spin physics. It is a point defect in diamond, which has triplet ground state and excited state, coupled by strong optical transition, allowing you to polarize electronic spin and also read out these spins. Moreover, the cross-section of optical transition is very high, and that's allowed to detect color centers at single defect level. So you even can see individual impurities in diamond. And that actually was initial property of these color centers that attracted interest about 20 years ago, because you can see single impurity atoms as here on the left side. This is an array of NV centers imaged in a confocal mode. Every spot here corresponds to emission of individual NV center, and you can control this location of these impurities with nanometer precision. Moreover, you can get also spin contrast, so the fluorescence intensity of this defect depends on the spin state, and if you shine a resonant microwave, resonant with spin transition, you get a drop in fluorescence. It's about 30%, and that's give you access, optical access to the spin state. You also can do many coherent control experiments, like for example, Rabi oscillations. You can excite coherent superposition of this center, and it's interestingly lives quite long for solid state system. Even under ambient condition, phase memory time of spin coherence, in this case electron spin coherence, is about a millisecond. And so this long coherence time is very important tool for many applications, from quantum information science to quantum metrology and quantum sensing. You can imagine doing basically sensing experiments sitting on the fringe of this FID, and if you apply a magnetic field, fringe pattern changes, and that's allow you to monitor magnetic fields with very high sensitivity on one hand, but also with high spatial resolution, because you can control individual atoms. Now I would like to touch a little bit now more specific applications, how we can apply this magnetometer for detecting NMR signals. And the main idea is that you bring this magnetometer very close to nuclear spins and detect magnetic fields associated with nuclear spins. And if you have this tool at hand, you have to use basically ability to bring your detector very close. You are not detecting now here induction, you are really detecting fields, and magnetic fields of nuclear spin decays quickly with a distance, but if you get very close, even a very few nuclear spin produce enough signal to be detected by these color centers. Very few, and that's why these NV centers are interesting for NMR at nanoscale in particular, particularly promising research happening. Now, how to make a spectrum analyzer out of this magnetometer to detect NMR signal? We want to tune this magnetometer to a Larmor precession frequency region, and that can be done as it was shown by Stuttgart group led by Jörg Frachtrup. You can do it by applying trail of pi pulses on the electron spin. These pi pulses refocus static noise and leave the NV center to be sensitive only to one particular frequency that is matching the space in between pulses. So you get a kind of sensitivity function shaping, and you can tune the sensitivity function spectrally by changing time between pulses. So the spectrum of hydrogen liquid deposited on top of diamond with an NV center located just a few nanometers from the surface is shown here, and it's a noisy spectrum, but remember now the sensing volume is just a few nanometers. In this case is about 10 cubic nanometers, very few nuclear spins, and the field itself coming from this very few nuclear spin is not very small. It's actually about 3 microtesla. So the few nuclear spin produce field of few microtesla because you get with your sensor so close. And that's interesting tool. And another interesting aspect here, that sensitivity does not really depend on the field, on the external B0 field. So you can also work in low field regime. In this case, we were using stochastic polarization, overshoot of spin up or spin down, and that's always happening. And this overshoot is about square root of n, where n is number of spins. Now, what is the current status with this detection of stochastic polarization? So we can now detect in total number of spins on the order of from a few hundreds to a few tens of thousands, depending on the depth, on the NV center, and a sensing volume. Polarization itself for this mesoscopic ensemble is about 1%, and it's not dependent on field, so you don't have to do too much to create this polarization. Spectral resolution that was initially limited in first experiments by coherence time of NV center was improved a lot, and now is not limited by NV center itself, so it can be on the order of a millihertz, but owing to a very small sensing volume and fast diffusion of molecules through, the spectral resolution is often limited by the diffusion of molecules themselves. And typically for this 5 nanometers cross-section of sensing volume, we have about 10 to 20 kilohertz line width. And that's, of course, a limitation if you want to go to a high resolution NMR. So the way to improve this is essentially hyperpolarization path. In fact, it was proposed some time ago, and now there are a few experimental efforts in this direction. You can use NV centers not only for detecting nuclear spins, but also for creating hyperpolarized ensembles of nuclear spins on top of NV centers. Since NV centers can be created very close to a diamond surface, a few nanometers, you can quickly transfer polarization to nuclear spins and then reset your NV center, repeat these experiments many times, and in this case, NV center can polarize many nuclear spins. So that's a bit different from dissolution DNP, where you have one electron spin sort of transferring polarization to a nuclear spin. Then you need to wait long time to get this electron spin reset. In this case, reset is done optically, so it can be done within a microsecond time. So within 1 second time, for example, one electron spin can polarize a lot of nuclear spins around. So one point to mention here is, of course, a polarization transfer technique. Electron spins are not resonant with nuclear spins, and this is known problem in the field of DNP. There are several tools available to enable this transfer, and one of these tools is essentially matching via driving the electron spin. If you drive your electron spin in resonance, you create kind of a new energy scale, rest states of a driven system. Driven electron spin can be resonant with nuclear spin, and you get enabled polarization transfer technique that works for conventional NMR, and that was also applied previously for spins inside of diamond in case of NV centers. In collaboration with our Curie team, we applied this technique to external nuclear spins of liquid deposited on diamond. And here I show you polarization transfer spectrum from NV center to external hydrogen spins. Hydrogen spins now have a Larmor frequency at about 2.8 megahertz. And when you drive your NV center spin during a spin lock-in pulse, matching the Larmor frequency, you lose polarization of the NV center electron spin, so fluorescent drops, and that's a signature of polarization transfer to external nuclear spins. So now you can also look how fast it is. I mentioned it before that you can do it fast. You can reset NV center fast, and if the distance is small, this polarization transfer can happen at a kilohertz or faster rates. And so here are two examples of dynamics, how NV center loses its polarization as a function of time. So for 3 nanometers NV centers, you can get polarization transfer rates on the order of 100 kilohertz here. So in first time of this of 10 microseconds. So you can polarize a lot of spins within a second. And if T1 time of nuclear spin is long, so you can attempt to detect this polarization, and that so far was not so easy because liquid diffuse, and so this polarized spins essentially are not anymore in a sense in volume, and so that basically is a challenge at the moment to detect this polarization that you created. So NV center can polarize many nuclear spins, but to capture this nuclear spin is remaining a challenge. And so here I would like to show you a few tools that we developed to enable efficient polarization transfer, but also detection of polarization. One is polarization transfer sequences that are robust to fluctuations of the driving fields. So you can essentially replace your lock-in pulse with the echoes, where the timing again is defined in resonance condition. In this case, echo sequence can be very robust against fluctuations in power of your microwave amplifier. And so such a echo that was developed to mimic flip-flop Hamiltonian was applied and shown to be very efficient. So here is this echo-based polarization transfer technique compared to conventional continuous drive. So continuous drive works very well, but you need to very precise matching conditions. In the case of echo, you are very robust. You can also have a detuning between your driving frequency and Larmor frequency of nuclear spins. So another point is basically detect this polarization. And so this is a collaboration between our team at Ulm University and Envision, our startup company focused on development of polarization techniques, team led by Philipp Neumann and Eli Schwartz. And I would like to show you a few very preliminary examples of detection of polarization created by NV-Center outside of diamond. So in this case, in order to improve the sensitivity, we've been working with small ensembles of NV centers, not with single NV centers. Instead of this array of single sites, single color centers, we had a spot containing a few tens of thousands of NV centers, and that was implanted in an area about 20 micrometers. All NV centers are very close, so they're distributed in space, but they're all very, very close to the diamond surface. We deposited a sample, in this case polymer, to avoid diffusion, and so we also added a technically kind of important tool, RF drive, to be able to control coherently these nuclear spins by external fields. Now, this is example of drive of these nuclear spins in these mesoscopic ensembles. Now we can essentially create the state of the nuclear spins correlated with the state of NV center, apply radio frequency pulse, and then detect the nuclear spin state again by NV center, not yet hyperpolarized, but now we can drive these nuclear spins. So this is a stochastic polarization with resonance RF drive, and we can define our pi-half pulses, pi pulses, and now get a full control on external nuclear spins. So this is still this 1% polarization, stochastic polarization we discussed before. Now we could apply polarization detection sequence that is not sensitive to this stochastic polarization and only sensitive to real polarization of nuclear spins. So this is done basically by preparing nuclear spins in hyperpolarized state. So we do this echo-based polarization transfer technique. Then we apply RF pulse, pi-half pulse, and then detect FID. And then to make it sensitive only to real polarization, we vary the phase of the RF pulse and detect the fringes. So stochastic polarization, owing to its stochastic nature, is basically get averaged out as a signal, and only real polarization survive and somehow give a signal to FID detected now by NV center. So in this sequence, NV center is used for hyperpolarizing spins and then detecting them. And so the signal that you see here, this fringe, is related to real polarization of external spins outside of diamond, polarized and detected by NV centers. So these signals are at the moment not very large. We are still suffering to improve it, and we need to understand dynamics of this polarization. Here you see how polarization build-up is observed. So we do see that for the first 10-20 milliseconds, we do see a build-up of polarization, but we only reach about 0.1%. And then the signal somehow saturates, and we do think that this saturation is related to sources of noise leading to shortening of T1 time of nuclear spins at interface, because we are sensitive here only to interface spins. We might have some residual diffusion of polymer. We do have a spin diffusion, and all these factors kind of can lead to saturation of polarization, and this is the current topic of research to unravel this mechanism and improve this polarization outside of diamond to values more closer to 10% or above. So with this, I would like to highlight the perspective of these fields. So I think these tools of nanoscale NMR are very interesting in terms of combination with zero field. The experiments I was showing are not really in zero field, but in low field, but they are applicable to zero field, as was shown also by Dima Butker with new protocols. The polarization of external spins at nanoscale can be very interesting in metabolic NMR and nanoscale NMR applied to biosystems. Finally, the detection by NV centers can be combined not only with polarization by NV centers, but also polarization or hyperpolarization by conventional techniques, more conventional techniques like parahydrogen-induced polarization or dissolution DNP. And there are some new developments in this field and recent publication by Ron Wolford group. And finally, in order to reach a real benefit, we also need to develop high-resolution detection tools. And there is a poster today, poster number 14 by Anjusha about super-resolution nano NMR. So with this, I would like to thank again our team in Ulm and collaborators and open for questions.
Thank you very much, Fedor, for this fascinating talk. I'm going to start with, well, I think there's some feedback. Anyway, thank you. So you've shown some spectra of the measurement of the proton frequency using this echo sequence. And I've seen that the frequency was in the order of megahertz. And I was wondering what dominates the frequency of the proton in this case, because if it were Zeeman interaction, then it would be, yeah, you would be at hundreds of millitesla. So what is this that dominates?
The experiments I was showing was performed at moderate fields. So this 2.8 megahertz is just the Zeeman frequency of protons in this case. So that defines the frequency. And in this particular experiment, the spectral resolution is too low to see any chemical shift.
Okay, thank you very much. So we have plenty of questions. I'm going to take them in order. So we have a question. Does NV center measure statistical polarization at ultra-low field? Then in this case, what is the Larmor frequency in the kilohertz range? I think it's similar.
Yeah, exactly. So the experiments I was showing mostly was done at a few tens or a few hundred Gauss fields. So in all these frequencies that were shown were in this megahertz range, it's just a normal Larmor frequency. So far we haven't measured spectra at zero field. Yeah.
Okay. Then how does the polarization level change depending on the liquid you measure? That is, why did you choose oil instead of water? Is it due to viscosity?
Yeah, so the first experiment to detect external liquids were done in oil just because it's kind of simple and it's it diffuses slower through detection volume. So the spectrum you measure is sharper, so it's easier to detect. And for polarization transfer, we have chosen in the very end the polymer to avoid diffusion, to avoid basically that polarization disappear over into diffusion. In this case, it was a polymer. So the nuclei remain in a sense in volume.
Okay. Then we have Roman asking, is there any difference in the microwave used here compared to the one used, for example, in dissolution DNP to transfer polarization from the electron to the nuclei?
Yeah, so I'm not very big expert in dissolution DNP, but in principle it is the same. So the only difference in nanoscale NMR is that you are somehow relaxed in terms of homogeneity of the driving field specially. So because you only have one NV center, so a simple wire produces enough homogeneous field to have no problem with the gradients. But if you have a temporal drift of power, it's still a challenge because now your matching condition might kind of be perturbed by your amplifier gain drift. And so that's why it's important to have robust sequences. But in principle, in this nanoscale NMR, you can be very efficient because you can drive your system with very, very small microwave structures. and there is not so much difference compared to conventional EPR drive.
Then we have James asking, I missed how you extract the NV-induced polarization level from the background statistical polarization level of 1%.
Mm-hmm. So we constructed the sequence in a way that it doesn't see the statistical polarization. So it was basically FID, and we basically changed the phase of the RF cycle pulse that induce FID. In this case, sort of you will start to change the phase of your FID, and if you go over 360 degrees, it will average out to 0 for stochastic polarization, but for real polarization, you will get a fringe. So you could basically choose detection system or detection sequence to be sensitive only to real polarization, not the stochastical one.
Okay, we have Emma asking, could you talk more about these noise sources that are causing the hyperpolarization to saturate so quickly?
Yeah, so it's still a kind of it's open question. What are these noise sources? We do see that polarization transfer efficiency saturates after a few tens of milliseconds. In a bulk, the polymer do have a very long T1, and so there is some discrepancy. So it looks like the nuclear spin just near the interface might have a shorter T1 time, and that might happen because you do have some radicals on the surface, some electron spins. Those can be short-living, and they create a kind of a spectrum that partially overlap with nuclear spin. This is one effect, and the second is, of course, directly spin diffusion. So the nuclear spins are very dense. You have a spin diffusion that also lead to loss of polarization near the interface. So in this case, in vCenter was detecting polarization just near the interface. And so if you have a spin diffusion, your polarization is not lost, so it diffuses into sample, but in vCenter below doesn't detect it. So we are not sure what is the dominant effect in this case. So the spin diffusion also happens in this time scale, so tens of milliseconds.
Okay, so we're going to take a final question by Gavin. How have you analyzed your diamond surface in order to understand its structure with, for example, STM or LEED?
So I'm not 100% sure I understand the techniques that have been, but I think it's kind of surface characterization techniques allowing you to understand the groups that are present. So what we ourselves didn't made it, but there are other groups that were characterizing diamond surfaces, and they have seen dangling bonds, for example, on the surface, and those can be sources of the relaxation. Furthermore, so we think that in vCenter itself can be ionized, and so there are some basically radicals that can be created during these experiments by vCenter itself, just near the interface, but so it's not 100% clear.